Hi, my name is Chiao-An Yang. Today I'm going to present our work, Soft Ranking Threshold Losses for Image Retrieval. This presentation is divided into 4 sections, namely the introduction, the approach, the experiment, and the conclusion. Our work focuses on the task of image retrieval, which has been a popular topic with the potential of enabling lots of real-life applications. Given a query image, the goal is to find corresponding images in a gallery set that either have the same class label as the query image or are visually similar to it. A common training practice for image retrieval is to first project all training images to a feature space, i.e., feature extraction. Then it deploys a distance metric to measure the distance between the features. The goal of the distance matrix is to minimize the distance between features with the same labels while maximizing those without. These distance metrics mostly suffer from the problem of requiring a predefined hyperparameters in order to perform expectedly. Take the widely used triplet loss as an example. The loss asserts that the difference between the distance of an anchor positive pair, DAP, and the distance of an anchor negative pair, DAN, should be larger than a given margin M. Here the margin is a preselected hyperparameter. Since the distribution of these distances varies from batch to batch, the ideal margin M would also vary, making it difficult to be predefined. One solution to such a problem is to explore the information of ranking. The ranking value, which indicates how an element is related to others in a list or set. Compared to distance, the distribution of ranking is uniform and bounded. It is easier to choose appropriate hyperparameters due to their fixed range. We propose to utilize such ranking-based machine learning and introduce a soft ranking threshold loss, the SRT loss. The approach section contains 3 subsections. We will first elaborate on how the vanilla version of SRT loss is designed. Then we will propose 2 extensions, the hard threshold and the ranking margin, which both further improve the performance. Here is a simple visualization of the ranking values of a given input list. The input is misranked, which means that not all the positive samples are the closest to the anchor. Our goal is to transform the misranked list into a well-ranked list. We designed our loss so that all positive sample ranks should be less than a threshold T+, and all negative samples ranks should be greater than a threshold T-. The obvious choice for the value of T+ is the number of the positive samples in the batch, which is Pi. The obvious choice for the value of T- is Pi plus 1. Combining the 2 terms, we can get the ranking threshold loss. However, the ranking value itself is not differentiable, so this version of loss would not work. In order to make the loss trainable, we use the soft approximation of the ranking value by replacing the step function in this calculation with a sigmoid function. We then replace the ranking values in the previous equations with the soft approximation. And finally, we can derive the soft ranking threshold loss. Now the loss is trainable. However, the approximation errors that come with the introduction of soft ranking cannot be easily ignored. Hence, we tackle this problem by proposing the hard threshold technique. Here is an example of how such approximation errors could affect our loss performance. The upper figure demonstrates a case where the errors are small and negligible. The lower figure shows otherwise. The order of the soft ranking is the same, however the values are not. If we use the same threshold T+, the positive sample here will not be considered misranked since it is less than T+. The sample will not contribute to the loss, violating our goal. It is critical that we introduce a harder threshold for T+, so that these misranked samples can all be correctly identified. Vice versa, a harder version for T- should also be introduced. By taking the approximation errors into account, which comes from the difference between the step function and the sigmoid function, we can derive that the harder T+ should be Pi over 2, and the harder T- should be B plus Pi plus 1 over 2. The math calculation here is detailed in our paper. Another problem with the soft ranking threshold loss is that only a few samples contribute to the loss. Consider this example, where only 2 misranked samples are selected and others do not contribute to the loss. Once the misranked are corrected, our loss is equal to 0 and the learning will stop. To have more samples contribute to the loss and force the network to keep training, we introduce ranking margins, including a hard one and a soft one. The margin M introduced to the threshold is said to be a hard margin when it's a fixed predefined constant. Here we show the example of margin M equals to 1. In addition to the disarranged samples, samples near the boundary also contribute to the loss. As for soft margins, we use the soft plus function sigma sp as an approximation of the rectify function. Since the derivatives of soft plus are non-zero everywhere, all samples will contribute more or less. We conduct our experiments on 3 person re-ID datasets and 1 fashion retrieval dataset to evaluate the capability of our loss. We compared our loss with these distance-based metric losses, including triplet loss, batch hard triplet loss, hard negative triplet loss, and adaptive weighted triplet loss. This table shows the comparison of our loss to the variance with the triplet loss on person re-ID datasets. All losses here are trained with the same backbone. Our soft ranking threshold loss outperforms all members in triplet loss by 3% to 5% in MAP on all datasets. As for fashion retrieval, our soft ranking threshold loss is better than or comparable to most other losses, except for hard negative triplet loss. However, the full version of our loss outperforms all losses. We propose a novel loss function using the ranking as input, with both a positive and a negative term, to assert the ranking values to satisfy certain adaptive thresholds. We introduce the hard thresholds and ranking margin as extensions for further improving its performance. Experiments on person re-ID and fashion retrieval benchmarks demonstrate that our loss outperforms other distance-based losses. Thanks for your listening. Have a nice day.